So, this is an overview of the lab. We drove in right here. Okay. So here was the ribs from the ship, and here was where the guard shack was. We came around here. So here's where the flags are, and now we went up to the top here. So if we look out that way, you're going to see, oh, and of course there's rain on the windows. You're going to see some of the original beam lines.
Hey, look,
so we would send protons.
Come over here,
You see where the steel pipe is on the stainless steel on that thing? It's a little bit of raised earth to help with shielding the radiation. But the particles would go under that berm, straight out, and then some would veer off towards that blue arch. Okay. And others would go straight out underneath those big berms where the little blue buildings are out there, out to the experiments where they would collide with targets, and then all the spray out the backside would be collected by the various detectors to try to understand what it was. Yeah, so you can see.
So compared to the one in Palo Alto, which was built out of the
That's
battleship.
Yeah, that's a 2-mile long straight shot linear accelerator.
Yeah.
So it just does single shot like a rifle.
Okay.
Ours is a huge circle, and it goes around hundreds of thousands of times, a lot higher energy than the one at Stanford,
Okay.
and then goes shooting out to these endpoints where they can collide with stuff.
Okay.
And that's the thing we call fixed target, because it's a fixed target, the particle collides with it,
Gotcha.
and creates a whole lot of secondary particles off the backside that the researchers will study
How do you hold antimatter?
in a magnetic field.
That's how you hold
That's
it.
what you hold.
Okay.
Everything here is done with magnets. So from the diorama here, what happens is there's a small linear accelerator that's about 200 meters long, and it starts right here, and we'll walk past that. So it shoots the particles that are starts from a bottle of hydrogen. We take the electron off, shoot the proton.
Okay.
Okay, and when it starts here, it leaves a tiny little room with about 750,000 volts of energy. All right.
How many?
750,000 volts, 755,000 volts.
Oh my God.
Okay. So when it leaves that room, it enters the first accelerator, and it's going about 75% of the speed of light when it exits the first accelerator. And it's now gone from 750,000 volts to 400 million volts of kinetic energy.
Okay.
Oh wow.
400 million electron volts. Yeah.
I'm looking for
So it leaves here at 3/4 the speed of light and goes into this small booster ring, and in a 60th of a second, actually no, sorry,
Evan, listen.
30th of a second, it goes up to 99% the speed of light.
So do you know what the speed of light is, Evan?
what?
Do you know how fast
How
light
fast
travels?
Light. When you turn on a light bulb, have you ever noticed how fast it goes?
Instant.
How fast is it? Like that, right? Faster than that, right?
It takes,
Yeah.
what, 8 minutes for the sunlight to get here?
Yeah, 186,000 miles per second, and that's where you come up with a light year. You take 1 second times 60 times 60 times 24 to be able to get a
You're
day.
traveling at 186 miles per second.
It's some obscenely large amount of distance.
Okay, so after the particles go 99% the speed of light, we transfer them down here to this machine. Now this is my specialty right here. And it's called the main injector, and it's a very dynamic machine. It's used for a lot of different things. So particles come in with an energy of 8 billion electron volts, and part of them will be accelerated up to 120 billion electron volts,
Oh wow.
which is 99.99% the speed of light. And we'll send some of them to a special target here, and the particles that spray off the end contain a large number of antiprotons.
Okay.
The statistics of getting antiprotons out of these collisions is about 1 for every 6 million protons that hit the target.
Okay.
But we're hitting it with billions. Or, hang on, we're hitting it with 8 times 10 to the 12. So, yeah, 8 trillion.